All right, everybody. Lecture 23. I was looking at my YouTube playlist because I was like, something isn't right because this is lecture 23, but I already had 23. Turns out I accidentally uploaded the last lecture twice, so whoops. But I just went ahead and corrected that. Okay, so this is our last lecture related to welded connections, and it's our last lecture before the exam. So after today, this is it in terms of the exam. Okay? Homework, this is actually, there's a typo here because 3.3 was graded and 3.4 still needs to be. Okay, 3.4. There's no 4.3. Okay. 4.1 was due today. I'm hoping that was really easy. The last homework before the exam is assigned today and it's due Monday. I'm not accepting any late work on this one because I'm giving you the solution right as it's due. So it's due Monday at 9 a.m. So Monday, we have our exam review. Come prepared with questions. It's on bolts and welds. Sound good? So you all know how I do exam review. Okay? Everybody get the code? I'm just staring at him. Okay. All right. Okay. Oh, and I found that video. I found that funny video. I have a funny video to show you. You'll like it. I have a funny video to show you. Okay. You'll like it? You want to get that?
Really hard to find it, so it probably is really good.
What's that?
I said you were working really hard to find it last time.
I know I found it though. There's a spot on the AISC web that it would have been, but where they got rid of Adobe Flash, they archived it, and I found it on there. I found it, so it's really cool. Okay. In fact, I'm probably going to show you this pretty early, here in a couple minutes. Okay. So just so we're clear, we have weld metal capacity and we have base metal capacity. These are the two primary limit states that we're using for strength checks. Dependent upon your grade, and your weld size, I'd say two limit states, but I guess there's really three of them because we have shear yielding and shear rupture, and we just take the minimum of these. Now these are all a function of the length of the weld. So in design land, what we're going to do is we're going to take the length of the weld to be 1 inch to get the capacity per inch, and then divide to get the total number of inches. Okay. Now, in order to do that, we first off need to determine the weld size, and we can do that through looking at minimums and maximums. And so minimum weld size is again based on the heat sink effect. That comes from table J24. Maximum weld size is based on plate distortion. In other words, if the weld gets too big, we start melting the tip of the plate, and that doesn't really, that's not really copacetic if we want to maintain the geometry of the plate and the resulting weld. Now, for designing welded connections, the design is pretty straightforward. So we determine our factored load. I guess I should mention that we can also design welded connections to develop the full capacity. We then choose a weld size based on weld limitations. And last time we talked about choosing the largest weld size up to 5/16. I'll probably highlight that here in a bit just to make sure that we're all clear about that. As why, but the long and short of it is when we choose the largest weld size, that results in the shortest weld length, okay? And then like I said, we determine the capacity of a single inch of weld, and we look at all of our limit states for that, and then we divide to obtain the total number of inches. Now laying out the connection, we have a couple of different ideas. We can either lay it out symmetrically or in a balanced arrangement. I'll show you that here in a little bit, and our example today is actually going to be balanced. And then we usually limit the weld lengths to the nearest inch. Now, as I mentioned, we have either, whenever we lay out the weld, we typically lay it out in either longitudinal patterns or longitudinal and transverse patterns. In other words, we never use only a transverse weld. Okay? Now, I told you last time that the reason for only using a transverse weld is because of ductility, okay? In other words, transverse welds are a lot stronger, but they are a lot less ductile. So if you're going to be conservative, assume the welds behave in a longitudinal pattern, right? Well, there is another issue associated with welding, and really just steel in general, and that issue is the idea of fatigue, okay? Now, I think I've mentioned fatigue before, but in case I haven't, if I were to give you a soda can, okay, and I were to say, okay, I want you to get the tab off of that soda can as easy as possible, what's the easiest way to get the tab off of the soda can? What's the easiest way to do that? Like if I wanted you to rip the tab off, what's the easiest way? You go back and forth and back and forth and back and forth. And after a while, it just kind of gets softer and it kind of just pops right off, right? Okay? Everybody know what I'm talking about, right? Okay, so the reason for that is because what you're doing is you're introducing micro cracks into the metal, okay? And as you wiggle it back and forth, you're applying a cyclic load, a load by cycles. You're loading, unloading, loading, unloading. And that concept of cyclic loading introduces the idea of fatigue. And fatigue happens whenever you have a specific detail, such as a bolted connection or a welded connection, or in this case with the soda can, you've got this riveted tab on top of the can. And if you apply a cyclic load, that cyclic load can introduce or amplify the effect of a flaw, right? That flaw can progress into a crack throughout the connection, and then the crack propagates and the connection fails. Now, without getting too far down the rabbit hole with fatigue, whenever we assess fatigue in bridges, we have a series of categories, and they're sort of like letter grades. So we have like a category A, a category B, a category C, and they get worse, right? So a category A is like bare steel. It's the best category you could have. And a category E is the worst. And category E is the category that you get when you have a transverse weld on the end of a cover plate. It's like the worst fatigue detail you could have, okay? And so to explain why transverse welds are a bad idea, I have a funny story about a McDonald's in Oklahoma. It's about aluminum, it's not about steel, but you'll see what I mean, okay? So this is from a conference presentation about a decade ago, and it's from a guy named Dwayne Miller, and Dwayne is the one of the senior research scientists at Lincoln Electric. So this guy knows welds. He knows welds better than like anybody, and he's got a really funny story about a welded detail. So I'm gonna pause this recording real quick. So, in fairness, though, the point that he's making about transverse welds is true, okay? That if you have a connection and you only have a transverse weld, it's about the worst fatigue category you could think of. So in bridge land, you never want to do that. Never. Because it will propagate a crack faster than any detail you could imagine. So the folks at McDonald's, hopefully they don't, or they fixed that since then. Okay. What's that?
They tore that down. I just Googled it.
I thought they were redoing it.
I think they tore it down from what I read.
Oh. That's a shame.
Because I was like, I wonder if that's still there.
I thought they were redoing it, but
Yeah, I think from what I've read, it's gone.
that's a shame.
It is.
It's still a funny story. They really fixed the problem by removing the handrail. Okay. All right. So going back to official business. Okay. So when we're in design land, remember that we typically want to choose the largest weld possible, not the smallest, because the largest weld size corresponds to the shortest weld length. Okay. So the idea is that if I have a weld that I'm designing, I ultimately want to provide an amount of weld area to resist that load. And I could use a really small weld size, but in order to get the same amount of area, I'd need one that's really long, okay? And that's going to take a long time to deposit, which means it's going to take longer for the welder to deposit, and that's going to take more labor, more money, okay? So we typically want the largest weld possible so we can get the shortest weld length. It's quicker to deposit, okay? Now, a common weld size used for design is 5/16 because as we mentioned last time, 5/16 is about the largest weld that you can deposit with a single pass, okay? So we mentioned this last time, but the idea is that if I have a weld, let's come up with some really, really large number. Let's say that I want a 3/4 inch fillet weld. There's no way to deposit that with a single pass. About 5/16 is about the largest weld that you can deposit with a single pass. So if you want something really big, like a 3/4 inch weld, you're going to have to do multiple passes of the electrode along the fillet the location in order to generate a weld of that size. So we really usually try and stick with the largest weld possible up to 5/16 so that we can deposit it in a single pass. Now, if the numbers just aren't working that well and you need a larger weld, that's fine. Just recognize as the engineer that that's going to take a longer amount of time to deposit. Okay, so so again, that's what I was saying here. I mean, you can deposit. Sometimes you may need to deposit a larger weld, but that's when the loads are pretty big, pretty large. Okay. Okay. Now this is something that's going to show up today, and this is the idea of a balanced weld arrangement. Okay, and so if you're just talking about a plate, welding arrangement's pretty easy. So when I say a plate, I'm just talking about like a lapped plate or something like that. So let's say you do the math, and let's say that the math says you need 23.72 inches of welds. I'm not going to deposit 23.72. I'll round it up to 24. 24 inches. Let's put 12 on each side. Done. Okay, that's fine for plates or for really any member that has symmetry. Okay, if you have an element that is not symmetric and you want to eliminate bending, so a good example of that is fatigue prone details. You want to try and eliminate any adverse bending effects. Okay, so if you want to do that, the idea is to deposit it like this. So for example, here's an angle. Okay, so if you have an angle, the centroid of that angle, the center of gravity, it hugs one leg. It's closer to one leg than it is to the other. So the angle is not symmetric. So the idea is that if the load goes through the centroid, the load is closer to the back of the angle than it is to the front, so we put more weld here than we do here. That's called a balanced arrangement, okay? And the way that we handle that is we sort of treat the beam or sort of treat the angle like it's a beam, okay? And we say, okay, there's a load right there. So the question is, what are the reactions right here necessary to resist that load? And then that's what we do. For example, if I have a table, right, and I'm sitting right here in the middle of the table, half of my body weight's going here, half of my body weight's going here. But if I sit over here a little bit, right, closer to one leg, this leg's got more load on it than this one does, right? So if I was thinking about this in terms of welds, this weld needs to be longer than this weld to resist that load. Does that make sense? Everybody with me on that? So that's what a balanced weld arrangement is. And we're going to do a balanced weld arrangement today to sort of demonstrate it. If you can do a balanced weld arrangement, you can do any welded connection that we're going to deal with in this class. So with that, let's go ahead and get to it. I have here a balanced fillet weld that I'm going to design to withstand a load of 150 kips, okay? And I actually don't have my calcs with me today, so we're going to do this one live. But I think you're going to find this is pretty straightforward. Okay. All right. Okay. Now, a couple things that we're going to do that we're going to need to handle. So first off, we're going to need to determine the size of the weld and then determine the capacity of a single inch. But let's go through a couple things. So we have A572 grade 50 steel. We're going to assume that that's used throughout. We're going to assume E70 electrodes. And what we're going to do is design this connection to withstand a factored load of 150 kips. Now, I guess what I should clarify here, because I just realized this isn't really clarified here on the problem, is that this is 6 inches, okay? In other words, what's happening is the angle is sort of sitting like that, right? The longer side is sitting down. So what we're essentially doing is sizing this fillet weld and that fillet weld. And I propose that this fillet weld right here, this one, is probably going to be longer. Okay? So let me kind of walk us through this, and I think you'll find this is pretty straightforward. Okay. So step one is usually to determine the factored load, but we know that. So let's just move right on to step two. And step two is to choose a weld size. Oop. Okay. Now, to be clear, we haven't been given the thickness of this plate, so we're only going to go off the thickness of this. And I think we need to recognize that the thickness is 3/8 of an inch. Okay, so 3/8 of an inch. Okay. Amen and Amax. Okay, so let's start off with Amen. Do y'all remember how to determine Amen? There we go. So table J214. So for a 3/8 inch thick plate, what is the minimum weld size? 3/16. Do I have a second on that? Okay. Now what about Amax, right? Bless you. Amax is either the thickness or the thickness minus a 1/16 of an inch, dependent upon this, right? And so we are certainly dealing with a plate that's thicker than 1/4 of an inch, so we're dealing with this. So what is 3/8 minus a 1/16? Hold on. 3/8 is 6/16. 6/16 minus 1/16 is 5/16, right? Okay, so based on a minimum weld size and a maximum weld size, what should we use based on these numbers? The larger, we go with 5/16. So we're going to choose A is 5/16. Now, let me ask you a question for the sake of discussion. Let's say what if Amen was 3/16 and Amax was 7/16? What would you choose? 5/16. Choose the largest up to 5/16, right? So what if that was the case? What do we choose? 1/4, right? Everybody with me so far? Okay. All right. Ooh. My screen's getting a little hoppy today. I don't know why. Okay. So for step 3, we're going to determine the capacity of 1 inch of weld. So in other words, we're going to take L sub W to be 1 inch, okay? And we're going to compute the capacity of a single inch to see if we can figure out the total number of inches, okay? Now, let's see if we can determine a couple properties. Okay, so we have the thickness, which is 3/8, A, which is 5/16, LW, which is 1 inch. Okay, what about FY and FU? $50 and $65. Okay, and that comes from table 2.4. Okay. Now, is there any other value we can glean from the problem statement? The electrode strength. Because that was given. We were told that the electrode strength is 70 KSI. Okay. And one thing I'll say is that if you don't know as an engineer, E70 is one of the most common. So E70 electrodes are probably fine for the purposes of figuring out a rough design starting out. E70 is a good bet. Okay, so what we're going to do is, based on this data, we're going to compute the capacity of each of our 3 limit states one by one, okay? So what we're going to do is, first off, let's do weld metal. Okay. And if you want, you could actually just leave the LW out, since we're taking LW to be 1 inch. So this is so what do we get for this? 6.96. Do I have a second? Yeah. Okay, so that's 6.96, 96, and I'll call it kips per inch, okay? So, in other words, that's the capacity per inch of weld, okay? And so we'll do the same thing for base metal yielding and base metal fracture, okay? So, okay, so we'll do base metal yielding and then we'll do base metal fracture. So remind me, what is the phi value for base metal yielding? 1, okay? And for a element in shear, for a welded connection, how do we find the gross area in shear? What is it? What?
I thought it was the same.
Well, it is. The net area and the gross area are the same, yes. But the actual means of computing either one of them is to take, yeah, you're right, yeah. Length times the thickness. So all I'm going to say is just the thickness, because the length is 1 in this case. So what do we got for this? Do I have a second? Okay. And then lastly, here, I'm going to move these over a little bit so it's a little easier to. Let's do base metal fracture and 0.6 FUA and V. So this is where you're saying, yeah, this area is going to be the same. The only difference is our phi value, which is, there we go. Okay, and so what do we get for this? Second? Okay, so we got this, this, this. Of these, which one governs? The smallest, because we're talking about a capacity. So therefore, okay. Okay. With me so far? Okay. So now we're going to lay out the connection. Okay? And I'm going to call this steps 4 through 5. Okay? So here's what I'm going to do. Since we have an angle, and since the angle is not symmetric, okay, I'm going to use a balanced connection. Okay, let me see something real quick. Okay, sorry. I'm going to use a combination of longitudinal and transverse welds. Okay? All right? And in order to do this, I do need a section property. Okay? Okay? In order to do this for an L6 by 4 by 3/8, I need to know where the centroid is. So what property for an L6 by 4 by 3/8 will tell me where the centroid is?
Is that your X bar?
Exactly right. Because here's the thing. Remember, here's the angle. Here's the neutral axis, and what I'm after is that dimension, which is X bar. So what is X bar? 0.933. Do I have a second on that? Okay. We are going to use that value here in a sec. Okay? So far, so good? Now, give me a little bit of breath because I'm going to draw a little bit of a schematic. Okay. Okay, so okay, so here's my angle, okay? And for the sake of discussion, let's put my centroid right there. Okay, is everybody okay with that? So all right. Okay. Actually, I just got thinking about something. Hold on. Wait a minute. Here's the angle, right? Okay. This centroidal axis is going like this. So I guess my question is, do I need X bar or do I need Y bar? I need Y bar, don't I? Because that's the dimension I'm after, right? So what is Y bar? I need Y bar. By the way, on the homework, I used an equal leg angle, so they're the same. So that'll reduce the confusion there. But yeah, we need Y bar. Okay. So to put some dimensions over here, this dimension is 6 inches. That's 1.93. Okay, does that make sense? All right, so I'll add this up here, that this dimension that's Y bar. Okay. All right. Let me do this. Let me, if it's okay, I'm going to scooch this over just a bit. I just want to have a little bit more room. Okay. All right. Now, like I said, I'm going to use a combination of longitudinal and transverse welds. Okay. So I propose that I'm going to place 3 welds. We'll call this weld 1. Call this weld 2. And let's call this weld 3. Okay? Now, this weld, I think, is shorter, right? Because it's further away from the centroid. Okay? So if this load is being applied this way, the welds are resisting load this way. So we'll call this F1, F2, F3. Okay, is everybody with me on that? Now, just so we're clear, how far is it from here to here? How far is that? What is this dimension from here to here? So if I just have a single weld that is 6 inches long, where would that force be acting? 3 inches. Okay. All right. Everybody with me so far? And by the way, let's not forget, that. Okay. Is this a fair schematic? Is that fair? Okay. Let's start off with F2. Can you tell me how could I compute what F2 is? What? Well, now hold on. F2 is a weld. How much capacity can a weld generate? 6.96 kips per inches.
So is it 6 times 10?
Exactly, because it's a weld that's 6 inches long. Which is what? Like, it can't generate any more than that, right? Do I have a second on that? Okay. So, how do I determine the remaining welds? How do I do that? How do I determine the forces? Well, I don't know about you, but this looks like a statics problem, okay? So what I'm going to do, I'm going to sum moments about the bottom, okay? And basically what I'm going to say is that everything rotating this way plus everything that rotates this way has to equal 0, okay? So the way that I'm going to handle that is I'm going to say from the bottom, F1 times 0 plus F2 times 3 plus F3 times 6 has got to equal PU times Y bar. In other words, F2 times its moment arm, F3 times its moment arm has got to equal PU times its moment arm. Obviously, this term goes to 0. And now let's just look at this equation. What's the unknown here? F3, because I know F2 now, and I know PU, and I know Y bar. So therefore, oh, sorry, that's not a plus. I just solve for F3, which is what? 25.87. Do I have a second on that? Do I have a sec? Or 25.87 kips. Do I have a second on that? Okay. So let me ask you this. What's the easiest way of now solving for F1? What were you saying?
Some of the X direction.
Exactly. Sum of the forces in the X direction. I think that's what you were saying, right? So in other words, if I sum forces in the X direction, I say that F1 plus F2 plus F3 has got to equal PU. In other words, everything going to the left has got to equal everything going to the right. So that means that just PU minus F2 minus F3. So 150 kips minus that's supposed to put a minus in there. And so what do we get for that? 82.37. Second? Now, this tells me the force required in each weld. Does that tell me how long the welds are? If you divide it by 6.96. So therefore, the length of weld 1 is 82.37. times that, and so what do we get for the lengths of L1 and L3? $11.83. And what about L3? 3.72. Sounds to me like this is my answer. And how did I get that? Just use 12 inches here and use 4 inches there. So what do we get? We get fillet welds that are all 5/16, right? Because we said that's the size we're going to use. They're all fillet welds, so upside down triangle, 4 and 12. And then 6 is because we welded this entire length. Does that make sense? That's it. Okay, if you understand that, then the homework problem is a lot easier. For one, it's symmetric. So when I say symmetric, I mean it's an L5. I think it's an L5 by 5. So no issue about which X bar, which Y bar, because they're the same. And then on that one, I'm saying it's only longitudinal welds. So because it's only longitudinal welds, you could literally use all these expressions and just set F2 to 0. You know. The only thing you'd have to change is, like instead of 6 inches, use whatever size the angle is and whatnot. So, does that make sense? Yes.
How do we know to use a transverse weld on that?
I said we were going to, basically. So in this homework statement, it says use longitudinal welds only. So I didn't say it in the beginning of the problem. I probably should have. So, but never use only a transverse weld. So unless you want to end up like McDonald's. Sound good? That's all I got, everybody. I'm going to pull up the code one more time, and I will see you all on Monday.